for sticking around. I know 2-day conference or 3 days if you've been here for the whole time. And yeah, my brain usually starts melting down by this point. So I'm going to be talking a little bit about monitoring, about how we use Postgres at Datadog, because we use Postgres primarily for our relational data stores. But just to kick things off, oftentimes I talk with people and I help a lot of customers with their monitoring needs and how to think about monitoring. And unfortunately, I think this is how a lot of people deal with monitoring, right? You just sit around and you're watching Twitter or you're getting customer feedback, and that's the way that you know something's gone wrong with your systems. So hopefully that's not you. But just to give you a perspective that we have at Datadog, we like to say that collecting data is cheap. If you take a look at how cheap storage is on your major cloud providers, you can store a ton of information for not much money if you're looking at things like AWS or Google or Azure. But not having that data when you need it. When something goes wrong, if you don't have that data, trying to backtrack and backfill that data to figure out what went wrong can cost you a lot of money on top of the cost of outages. So just to give you an idea of how much money that is, if you're comparing the cost of storage, a couple $1,000s for gigabytes of storage, Aberdeen Research Group published a study a few years back, and they said that small companies on average lose about $9,000 every hour of outage or incident time that they have. Medium companies lose $215,000 an hour, and large companies lose roughly $900,000 an hour. So if you're wondering about the cost of monitoring, the cost of storage for your metrics, I think that's a pretty compelling argument to have them. A little bit about me. I'm Jason. I work as a technical evangelist at Datadog, which means that I primarily do what I call docs and talks. So I help write our technical documentation. I help explain that and educate our customers and just general people in tech about how they ought to think about monitoring. And then I also come to conferences like this and I present about monitoring topics. Datadog is a SaaS-based monitoring platform. So we have thousands and thousands of customers, and we ingest all of their metrics and their logs and their APM traces and provide them with an easy single point of access, single pane of glass where all of their staff can log in and get that data, receive automated alerts. To give you an idea of the scale of what we handle, we do trillions of points of data every day. So just in the time that I've started this talk, we've handled hundreds of millions of points of data. We are hiring, so if you're here and you're interested in monitoring and you're looking for new challenges around how to build infrastructure at scale and help other people monitor, we are hiring. So that's the link for that. But as I mentioned, the talk is primarily going to be about how we scale Postgres and how we monitor Postgres at Datadog. As I mentioned, Postgres is our relational database of choice. So within Datadog, we use Postgres primarily, and then we use Cassandra for all of our NoSQL needs, and we use Redis for a lot of our caching and queuing systems. And just like most people, when you start off with Postgres, you're not a big company, right? So Postgres is a really easy thing to install. It's open source. You set up a Postgres server, and then suddenly you're faced with that notion of how do I scale this? And so off the bat, scaling, you're like, well, let's just make it bigger, right? Let's get more memory, more CPU, more disk. And you very quickly realize that scaling Postgres is not just that easy. Like at some point, you reach a maximum limit. You can't get a 5 petabyte system, 5 petabytes of memory, or like all the storage in the world. So you have to realize that you start to scale horizontally, right? And so for us at Datadog, like I said, we use Cassandra for our NoSQL, and Cassandra is built for this idea of just add another node to the cluster, and it automatically does the replication, and it's good with things like multi-master. But the notion of Postgres is it's a little bit more, I don't want to say complex, but you have to think about how you're going to scale your Postgres a bit more. And part of that involves you want that strong consistency. That's one of the reasons that we love Postgres. So this is a pretty standard architecture that a lot of people use to scale Postgres. Essentially, you have a single write master. So all of your writes come into one machine. that replicates out to a pool of machines or read replicas. And so now you're able to optimize your write master to receive and write that data. And then you can scale those read replicas up. So as you're reading more data, you simply scale more machines. And it's a very efficient way to do things. Aside from the benefits of you being able to manually optimize some of these things, Postgres has a lot of built-in ability to optimize as well. So it really is a very efficient way to do things. So when we thought about building our system, we had some requirements, and they're pretty straightforward requirements, right? If we have a system like this, your requirements are that your write master has to remain writable. You always have to be able to write to that machine, so pretty straightforward. And your read replicas have to remain readable. So again, these are not very hard concepts. But then as you start to replicate, one of our other requirements is that your read replicas have to stay up to date. They can't lag too far behind. So if you're in our business with monitoring and you're ingesting metrics from one end and then trying to display those to people or trying to send automated alerts, if there's a lag between when you're receiving that data and writing it and something in our back-end systems can read from it, well, then now people are getting delays in the alerts that they need, and that's not a good thing. So we want to ensure that those are up to date and they don't lag. And then additionally, like I said, the idea behind building out replication pools is to be able to scale easily. So the other requirement is that it's got to be super easy to have new instances of read replicas, to scale that up as we need them. So all this said, what tools do we use? Well, the tools are actually pretty straightforward. Postgres handles a lot of the replication out of the box. And then the other tool that we used was WAL-E. WAL-E being WAL, the write-ahead log. And WAL-E was a tool that was developed by the team at Heroku. So again, Postgres handles all that replication. That's the link to the docs. They're really good docs as someone who writes documentation for a living. But WAL-E really has four main functions: backup fetch, backup push, and wal fetch and wal push. And so we use this to be able to make backups really quickly. And then with our systems, we can, if we need to instantiate another read replica, we can get that up and running really quickly off those backups. So WAL-E actually is not what we use now. We use WAL-G. So WAL-G was actually a rewrite of WAL-E in Golang by Daniel Farina and Katie Lee. So Daniel Farina is the original author of WAL-E. He now works for Citus Data. And Katie Lee was one of their interns. So they actually invested in an intern, spent a lot of time, rewrote it. And the performance on WAL-G is amazing compared to WAL-E. I think on the benchmarks that they produced, and we haven't run them on ours, other than anecdotally, we've noted that it's faster. But I think on the ones that they ran when they first wrote it, it was something like 4 times faster, just out of the box. So the nice thing about using WAL-E or WAL-G, though, to produce your backups is when we're thinking about having these replica pools, if we want to instantiate another replica, we can really just take that WAL backup and use that to bring that replica up to date to the current day, since we do daily backups. And then it's not actually impacting the write master. It doesn't have to receive those WAL logs until just catching up that last little bit. So it allows us to catch up further. But this is actually what our architecture looks a little bit more like today. So not only we have that write master that everything's coming into, we have a number of hot standbys in case that write master were to ever fall over. We can almost instantaneously put one of those standbys into production. And then when it comes to the read pools, we actually have multiple pools. So one of the things when you're having a read pool is if you have one giant pool and all of your applications or all of your services are reading off of that, there is the ability for them to impact each other. If something becomes very write-heavy, it can start using more of those resources. So we actually break things out into multiple read pools, and each of those is dedicated to an application or a service, and that allows those to scale independently as those services or applications need them. So that's a bit of how we're set up. Let's take a step back and talk about how we think about monitoring, before we jump into the actual specifics of how we monitor this. So at Datadog, we like to think of metrics as having 4 really good qualities and things that you need to be aware of as you're monitoring. Whether that's using our tool, whether that's using open source tools, you need to keep all of these things in mind. And the first is that your monitoring tool, or the metrics that you're gathering, needs to be well understood. So there's this story, this ancient story of the blind men and the elephant. And as this parable goes, there are a bunch of blind men, and because they're blind, they've never seen an elephant. So they encounter an elephant, and they're all standing around, and they reach out, and they're feeling different parts of the elephant. And so one blind man reaches out and grabs onto the tail of the elephant and says, oh, the elephant is thin and wispy like a small snake. And another one reaches out and feels the side of the elephant and says, oh, the elephant is big and broad. It's like a giant wall. And so there's this misunderstanding of what an elephant is. And oftentimes this happens with our monitoring tools, especially as we break up into teams. You have one infrastructure team handling a specific service. You have a developer team handling a particular application. And getting everybody to meet together and have a shared view of monitoring, a shared view of what they're looking at, and how that relates to the other parts of the business or the other parts of the business application can be difficult. So when it comes to monitoring, getting everybody on the same page and ideally having a central point where people can understand the metrics that they're looking at with relation to the entire business application. The second quality of good metrics that we absolutely need is sufficient granularity. So I particularly like the Winter Olympics. One of my favorite sports is the men's speed skating event. And we can see here some of the scores from that gold medal or that final race. And so for this one, we see that Norway came in at 34.41 seconds. Korea came in shortly behind at 34.42. We inherently understand that when we're looking at things, particularly metrics, that it matters on the resolution, right? If I had said that our resolution for this race was on 1 second increments, well, congratulations, all 5 of these gentlemen would have won gold medal because they all finished in 34 seconds. So we realized that we need sufficient granularity. And when it comes to our monitoring tools, that's something that I think a lot of people miss because we can see here the difference between 1 second granularity. So we've got that CPU spike. It happens to spike out at 46.67%. And it happens at 2 p.m., 6 minutes after, and 16 seconds. So pretty understandable, but there are a lot of metric systems because they're trying to save on storage costs. They're trying to roll things up that they move to 1 minute granularity. So you see this a lot of times with your public cloud providers. AWS, Google, Azure, all of those by default will do 1 minute granularity. With 1 minute granularity, what do we see here? Well, our CPU spike dropped to 36% because it got averaged down. And it shifted. So it's not happening 16 seconds after the minute. It's happening on the minute. So if we're thinking about if this is a problem, where do I now take this information and look in my logs? What maybe web request does this correspond to, or series of web requests? And again, people start to try to save money. So if you're looking at public cloud providers, they'll start to roll up even further as you push beyond 1 day or into 1 week. And so sometimes they'll go up to 5 minutes or even 1 hour. And we can see here that obviously at 5 minutes now, we're averaged down to 12%. And we've, again, pushed that time marker to the start of that 5 minute block. So I always suggest to people that the best way to have continuously reliable high uptimes is just to have really big granularity, right? If we set our granularity to 5 minutes, we'll almost never have an outage. That's a joke. So the third quality of good metrics that we absolutely need is that they have to be tagged and filterable. So we used to think of a metric as this. It's a thing, what is it, or a name. And it's a value of how much, right? And then it's a timestamp of obviously when it happened. And as we start to build our systems, particularly as we're looking at how we've architected our system with Postgres of having multiple replication pools and being able to spin up a lot of these, we need this idea of tags, of where did this come from? Because if we don't have that, then it's hard to separate out that information to know exactly what's going on. And so when we have those tags and we tag on things like the role or the place that this came from, not only application-wise, but where in the world, what availability zone, what cluster did this come from, you're able to ask more interesting questions from your metrics. So rather than just being able to see requests per second, you can see, requests per second from a particular application using a particular piece of software, comparing one region to another. So you can start to understand what's normal, what's not, and how your different zones are responding. Something that goes hand in hand with this is the fourth quality of good metrics, and that's that your metrics have to be long-lived. You have to keep things around long enough so that you can understand the context and understand what's normal. So if I were to ask you with this particular graph of data, anybody see the pattern here? It's kind of hard to see what the pattern is here, but if we keep things around longer, and hopefully that's a little washed out, but maybe you can see the groupings now. But as we keep data around longer, we can understand what those patterns are. And if I were to do something like this, now we can actually understand with our data what's going on, right? We wouldn't be able to look back if these are weeks. We're looking back 3 weeks in time, but we're also have enough history to understand that normally we have something, a spike every single day. So being able to keep your history around for a long time allows you to apply things like algorithmic operations or machine learning or all of these other tools that help us spot things that aren't apparent to the naked eye. So that said, we've got those 4 qualities of good metrics. How do we think about them? How do we use them? So we like to have a framework, and our framework really groups metrics into 2 different types of metrics, and then events being a third. So the first type of metric is work metrics. And work metrics are really your high-level business metrics. These are the things that matter to your company. I particularly like donuts, so I'm going to use the example of a donut factory. If I own a donut factory, my work metrics, the things that matter to me are how many donuts am I producing off the line, right? My throughput. Success would be how many of these donuts are properly glazed. They're actually baked all the way through or fried all the way through, and I can sell them versus errors. How many of them have a defect and I have to throw them away? So they're a measure of my overall performance. If I'm thinking about the next type of metric, well, that's resource metrics. And those are the things that are underlying and support my top-level work metrics. In the case of a donut factory, these will be things like, do I have enough of the ingredients that are necessary? Do I have enough flour, enough sugar? What's my overall usage rate of these? Do I have enough if I were to receive a spike? If we're thinking about the systems that we're building, these are the ones that, unfortunately, people focus a little too much on. These are things like CPU or memory or disk space, network I/O. They're important, but they're only important enough to support those top-level metrics of, is my application running? The third thing, which isn't actually a metric, but is very important in this framework, is events. And events are really the things that change around your systems. I like to point out Newton's laws of motion, and that one of them is that objects in motion stay in motion unless acted on by another force. And similarly with your systems will work just fine if they've been working fine until something happens. Code change, someone pushes new code, configuration change, things like that. So those are the events that you need to watch out for. So you have to start with those high-level work metrics as the important things, and then you can use the others to dig into it. Because this is often a question that I see people faced with, right? They focus too much on those resource metrics, and you ask them, are you losing money? Is your application actually working? If you're monitoring things like CPU and memory, those are okay for discovering issues, but you really want to page and alert on those high-level ones. Use the others to actually dig in. And the way that you do that is you start with that work metric, you figure out the underlying resources for that, and then you look at those events. What changed? If nothing changed, you can keep drilling in. That resource metric becomes a work metric for somebody else or a subsystem within your application, and you take a look at what are the resources that support that, what are the events that cause that. So all that laying the background of how we approach monitoring at Datadog, how do we actually monitor Postgres at Datadog? Well, we gather a lot of metrics. These are all of the things that come default out of Datadog's integration with Postgres. So there's a ton of stuff. You don't have to actually monitor everything here, or at least alert on it. You shouldn't. But these are all the things that we feel like are important enough that they should be defaults for us to gather. Now, I know that I said work metrics. You look at the resource metrics, those become work metrics. And for some people, that gets a little bit confusing, right? Because if resource metrics become work metrics, then really do we alert on everything? So just to break this down and show you how we do this, at the top level, your work metrics are your business. Are customers able to do what they need to be doing? So if not, who do you alert? You alert your leadership or the people that are responsible for that business application. Business applications are made of services, so that service becomes the work metric for developers or service owners, right? So if a service goes down, you alert your developers. Services are made of components, and this is where our Postgres team gets involved. That component, one of them, is Postgres. And so our team for Postgres is part of our ops team. We call it DRE, Database Reliability Engineering, similar to SRE. But their job is they get alerted if Postgres goes down or if it's not meeting the requirements. Postgres obviously runs on servers, so if it's actually a server issue, that gets dropped down to our ops team or our SRE team. So this is how we have things structured, and it allows us to drill down, and you can contact the teams who are required without sending too many alerts. So if we're thinking of high-level work metrics, for us with Postgres, what does a work metric mean for Postgres? And really, for us, that means availability. Postgres needs to be available. It needs to be able to read and write data. So if I turn back to the requirements that I mentioned earlier, again, these are very, very basic. Write master has to stay writable, read replicas stay readable. So if I take that first one, write master has to stay writable and read replicas have to stay readable. What do we actually alert on? Well, for these, it's pretty simple, right? They have to be available, so we use up-down checks. Is Postgres up? Is it down? If it's down, we send an alert. We also include latency with this, right? Because we realize that it's not just is Postgres up, it's is Postgres up and responsive. So these are the two high-level things that we alert on from those particular requirements. If I look at the next requirement, that read replicas are up to date and don't lag behind, well, what do we alert on for these? Well, we alert if the write master standby is available. Like, if it's available, great. If it's not, that should send an alert because you're essentially driving down the road with no spares. You have no possible failover. So we want to alert on that. The other thing that we alert on is that the write master standby replication lag can't be too high, right? If you have a write master and you have a standby that's ready to jump in, but that's delayed by a lot, well, if your write master falls over and you put that standby into production and you've now lost data because it was lagging, that's a bad thing. And then similarly, we alert on replication lag. So again, for us, if we're receiving data in and our replication pools that we read from are lagging far behind, then our customers aren't receiving alerts in a timely manner, so that's a problem. And the last bit that we alert on for this is for that last requirement. Additional read replicas need to be able to be provisioned quickly. So again, the way that we do read replicas is that we start with a WAL backup that we've produced from WAL-G, and we use that to spin up a machine quickly. So if that base backup is too old, well, that's a problem. We can't provision that machine quickly. So we do that on a daily basis. So we want to monitor to ensure that our base backups are 24 hours or less. So when it comes to the capacity or the resource metrics, we think of those as capacity. What are the things that support all of these things that we do? And those are really super basic. They're the things that you would expect: CPU, memory, disk, and connection limits. So do we have enough things that Postgres can run? So these, I think, are all really basic. They're basic ideas behind how you should approach monitoring. They're really basic ideas for how you should think of monitoring Postgres in particular. But one interesting thing that we do is we don't just want to monitor to ensure that Postgres is up and running, right? Keeping things up and running, that's the bare minimum of the job. We really want to take our monitoring and use that data to inform how we get more performant systems. So how do we think about performance? Well, I love this talk by Josh Berkus. If you take a photo of this slide, this is a good one to take. And if you've got some time after the conference and you feel like watching yet another conference talk, Josh has a fantastic talk about how you get performance. And he really lays things out to these 5 in this order. So oftentimes people focus on, let's tweak and tune our Postgres.conf. That's fun. Everybody likes to go and twiddle with settings. But really, the number one way to get faster Postgres performance is to cut activity. Find those slow queries. Find those queries that don't need to be run. And the second is to find the slow queries. So cutting activity is really easy, right? You can take a look at your query logs. For us, we have an APM application that will gather up all the queries that are being run. And we can see how many hits, how many times was this particular query run. And if it's run a lot, we can go check it out. Where is this being called? Why is it being called? Do we have that information? You'd be surprised at the number of times that developers will query for things like a user ID when they've already got that in a variable. So cutting that down is the number one way to get better performance, and we can actually monitor things like that. Slow queries, though, is actually, I think, the most interesting, because it's really easy to take a look at the queries that you're gathering, or take a look at the slow query log, and find a bunch of queries. But I think the problem this leads to is the slow query log. Everybody familiar with slow query log? Yes, maybe, sort of. I'm seeing some nods. If you're not, really, you can go and you can enable slow query log in Postgres, and you give it a time. And it's an arbitrary time. So you can say, every query that takes over 3 seconds to run, log that for me. And then you can go into the log, and you can take a look at that query and say, this one was slow. Let's take a look if we can make it faster. One of the problems with this, though, is that that's fairly arbitrary. What does 3 seconds mean, right? If we're thinking of performance, my view of performance is that we should be taking a look at not just the latency, not just how long something took, but the actual potential of that. So if I were to show you 2 queries, select star from tiny table where non-index column is something, versus select star from massive table where index column equals something, well, the second query, if it's a massive table, could potentially take over my arbitrary 3 seconds and show up in my slow query log, whereas my select star from tiny table that's not optimized could be really fast just because it's tiny, and so it'll never get caught in my slow query log. So we have to start thinking of new ways of what we consider a slow query or not. So one of the ways that we do that at Datadog is we start to consider things like RAM versus disk, right? So rather than an actual amount of time, what is this query actually doing? I love this quote from Rob Haas. He said that, so aside from shared buffers, the most important memory allocating parameter is workmem, and that raising this value can dramatically improve the performance of queries. Workmem is a setting that essentially controls how much memory is allowed to be used by a query. And so obviously, increasing that means that larger queries can fit into memory, and we all know that memory is much faster than disk. And so if you do that, you get much faster results. But people often stop there. They take a look at workmem, and they're like, great, this is currently at 4 megabytes, let's double that, or quadruple that. He notes that it's important not to overdo that. It's important not to overdo that because if you continually increase workmem, it's really easy to get your system into a state where it can just quickly run out of memory and then crash, because that number gets multiplied by more connections and the more times it's run. So our database reliability engineering team had this notion that just like goldfish, when you put a goldfish into a small bowl, it stays small. If you put a goldfish into a giant lake, it gets huge. They just grow to whatever size of thing you put them in. And so our DRE team thought about this and said, yeah, if we continue to increase the memory, our developers are just going to continue to write more complex queries and fill up that memory. And we're not going to get anywhere. So they had this notion of the way to actually find these inefficient queries was to reduce that memory. So we'd gone from the point of increasing it to get that to performance to starting to decrease it. And we kept decreasing it, smaller and smaller. And the thing that does is it forces queries to write to disk. And that helps us identify inefficient queries. Because whenever a query writes to disk, it means that either a configuration changed, and Postgres doesn't have the memory it needs. Well, we control the configuration, so we know if that were the case. Or it means that the amount of data in a table, what used to be able to fit in memory, that a query now requires things to go out to disk. And so that's something that we can monitor for, right? We can see what the size of our tables are, and we can start to optimize that. Or it simply means that a query got changed or a query got added, and it's not optimal. So it gives us an idea of what we can actually do to dig into that and to start to figure out the performance. So the way that we actually monitor this is with the temp bytes. Temp underscore bytes is the metric that you want to be watching for. So similar to the slow query logs, are you familiar with the explain or explain analyze function within Postgres? Not seeing nearly as many nods. So explain is a fantastic command within Postgres. Explain actually displays the execution plan. So if you have a query, you can say explain and the query, and Postgres will tell you, here's what I plan to do with this. Here's all the operations, how I'm going to join this, how I'm going to sort this. You can use that in conjunction with analyze. Analyze actually will take that and then run it, and then actually show the results for you. So this is a highly formatted version of what it will return. But if I explain analyze on something, it'll show me things like it's going to do a merge write join. And then after that, it's going to use the condition that UID equals another UID. And eventually, you get down, and when it's sorting here, we can see that it'll actually call out when it's writing to disk. So we can go from monitoring temp bytes and noting when Postgres is writing to disk. And if we have that fine granularity on it, then we can go and take a look at our logs, because we can run auto-explain. So auto-explain essentially will automatically run explain analyze for you whenever a query is run. So we can correlate those times, take a look into our logs, and then we just have to search for whenever this query is writing to disk. And now we know those queries that are writing to disk that we can potentially optimize. So that's the way that we really approach performance, taking a look at, trying to do the potential, where can we save by keeping things in memory. So just a quick summary of how you should be thinking about monitoring your Postgres. And the first is that you have to understand those differences between the work metrics and the resource metrics and events. So if you've got monitoring and you're setting up automated alerts, which you should have, set those up on your work metrics, the things that matter to your business, and then use the resource metrics and the events to start to hone in on what the causes were for that alert. But more than that, consider the potential, not just the latency. Slow query log is a great tool, but I think more often than not, it's used incorrectly because people just automatically set a time that's completely arbitrary. So start to think about, what does performance actually look like? How are we optimizing things? Can we keep things in memory versus writing to disk? Aside from the obvious, are we indexing the right columns? So think about performance in that sense. And then the number one thing for performance that I think is counterintuitive, but that we should all start to think about is, how can we keep smaller limits, smaller reasonable limits, but use those constraints and use those constraints against our developers to start having more optimal queries. Because we'll find that as developers have smaller constraints, they get creative and will build solutions to fit within those constraints rather than constantly demanding bigger and faster machines. So that's the crux of my talk. We do have a ton of other documentation and blog posts about how to monitor Postgres. Emily Chang, who's a technical writer for us, had a series that she published in December, and that's the first link, which covers all the aspects of monitoring Postgres. She recently published one on how to do it with RDS, because there are a few significant differences if you're running on AWS. And then it's funny, I've been sitting in this room listening to a bunch of other people talk about Postgres and everybody hating on Postgres vacuums. But she wrote a fantastic article about vacuums and when you want to run them, how you want to run them. They're there for a reason. They try to keep your Postgres nice and clean. So you should use them. Don't hate on them quite so much. And if you understand them better, I think people won't hate on it quite nearly as much. The fantastic people at Percona do want us to rate sessions. So if you have the app installed, feel free to rate my session. But other than that, I'm going to turn it over for questions if anybody has questions. And while questions are running, that's the link to the slides if you feel like downloading all of the slides. I know it's also available from the Percona app. And then I'll be taking questions now, but oftentimes you go home and you think of something, and you're like, I wish I'd asked that. So there's my contact info. I'm getbisect on Twitter or jason.yee@datadoghq.com. If you have any questions about your Postgres systems or about monitoring in general, how you should think of monitoring, or you just want to talk about technical things, feel free to shout out to me or send me an email. I'm always happy to help people monitor their systems. Is there an optimal value for workmem? There is, and it depends on your system. So workmem, like I said, it gets multiplied by the number of connections that are coming in and a few other things. And so it's a calculated, it's a value that gets multiplied and applied in ways. So really, it depends on how much memory you have. It depends on how your Postgres is being used. So I can't just say, like, everybody should set it to 4 megabytes, because that would be dumb. So yeah, it really does come into a factor of like how you're using Postgres, what you're using it for, what your system looks like. Our numbers, because of how we're using it and at the scale that we're using Postgres, are going to be much different from yours. So unfortunately, there's not a great answer to that. But yeah, minimum value, I think 4 is the default. Trying to remember, although I thought it got changed sometime last year. Can't remember. Yeah. Shoot me an email, though, and I'm happy to connect you with our DRE team, and they can provide more details on how they did the calculations and set it. Yeah. Any other questions? Cool. Well, thanks again for sticking around to the last session of the day. I guess